All right, so tonight is the last night of new material. So let me share the screen real quick with what we're going to go over. So you have 3 homeworks due tonight, 2.4, 10.1, and 10.2. Remember, that was a scatter plots, correlation, and regression. And I'll save the questions till the end of class. And then tonight we're going to do the last section, which is 11.2, which is on contingency tables in the chi-square. So let me stop sharing. Oh, I want to show you a couple things before we, come on, trying to get over to my other window. It's not working. Okay, I'll do it this way. All right, I wanted to go over to our class for a minute and just remind you that, hold on a second, we got a couple of people coming in. Marissa and Maria. Okay, so student survey of instruction, remember we talked about this last week, is now available, and I checked right before class, and you have to get to 23 to get your extra credit, and I checked before class and there were 17, so you need 6 more submissions to get the extra credit. So just a reminder about that. Your final exam, you're going to be taking it starting next week on Friday, which is May, I think it's, let me check the dates, May 5th, right? Yeah, May 5th through May 7th. You're going to take it with honor lock, and in your class, I know yours doesn't look exactly like mine, but the honor lock option is right up here on the top toolbar. I'm not going to click mine because it looks different from what you see. When you click that, you're going to see the honor lock sample test, and there's only been 6 people who have taken that. You have to take that in order to be able to take the final. And you'll see it, and then next to the, I think on the other side of the screen, I don't know if it's the right or left, it'll say launch. And you have to go through and do your ID check, your room scan, and then honor lock will insert the password into the sample test for you. You do have a module here on your table of contents about honor lock. Where's your honor lock module? Here it is, honor lock information that explains honor lock to you. And there is a video at the very bottom here if you want to take a look at it before you try the process, if you've never done it before, with a test in my math lab or my stat lab. This video shows you exactly what happens. If you are in there and you're having trouble, there's a chat option, there's live help available. So please use that link to help you get help while you're in there. I can't get into honor lock to help you, but their support staff will definitely jump in and help you if you have any issues with it. But you've got to take that honor lock sample test before you have access to the final exam, and also to the final exam prep quiz, because I want to make sure that you understand how the process works before you actually are getting ready to take the final. If you get that honor lock sample test done before 11 o'clock on May 4th, I will add 1 point to your final exam score. So that's an incentive for you to get that done ahead of time, because I don't want you to wait till the last minute to get it done. Okay. And there's also a final exam materials folder in here. And that's where it actually tells you if you get that honor lock sample test done by 11 o'clock on May 4th, I'll add 1 point to your final exam grade. All right, so any questions about honor lock, about the final exam? Next week in class is a review. And what I did was post here in the final exam module. Down the bottom here is a copy of the final exam prep quiz, which I put into a PDF format that we can go over in class together next week. Or you can bring any questions that you might have to class to get ready for the final.
What was the last thing you said about the May 4th?
Oh, if you get the honor lock sample test done right here by May 4th, I'll add 1 point to your final exam grade.
Gotcha. Okay, thank you.
Because I'm trying to incentivize you to get it done ahead of time, because I hate it when the weekend when the student's like, I can't know how to do it. The sample test is created so that the score doesn't count. It's just created so you understand how the process works.
Right.
Some of you have probably used honor lock to take an exam in my math lab, but it's a little bit different than taking an exam that resides in my courses. So it's a little tiny bit different. And I want to make sure you understand the process before you're actually starting to take your final. Okay. And you also have the ability to earn some extra points on your final by doing well on the preparation quiz. So if you score at least 70% on at least one attempt, I'll add 2 points. And if you score at least 80%, I'll add 5 points on top of the extra credit point for the honor lock sample test. So that takes
I'm sorry, can you repeat that real quick? My my mic.
Okay, she cut out. So if you can see the screen, I hope you can see the screen. In the final exam module, it explains bonus points available if you score at least 70% or more on at least one attempt on the preparation quiz. I'll add 2% to your final exam grade. If you score 80% or more, I'll add 5%. So that's like 2 extra credits going to your final exam grade. One based on the prep quiz and one based on getting that honor lock sample test done early.
Thank you.
And then you also have the ability to earn an extra credit point based on the student survey of instruction. All right. Okay. And also I mentioned, I think it was in the email last week or the week before, I can't remember which, all of your tests now in, let me go over to your My Stat Lab course. Let's pull up the test. In case you missed any of your tests here, whoops. I've extended the due date for all the previous tests till May 3rd, which is next Wednesday. So if you missed any of taking tests, unit tests 1, 2, 3, 4, or 5, these are now available to you. But you notice again, you still, my demonstration student hasn't done her homework. You still have to get the 60% on each of the homeworks. But if you missed any of the unit tests previously, this is your opportunity to make those up. And then you have one more unit test, unit 6, that'll be due next week.
I have a question. For the preparation quiz, is that on the Pearson Mastering Chemistry or is it on the course content? Because it shows it on the PDF file.
Well, that's the one we're going to go over in class next week. Can you see my screen that I'm looking at right now?
Yes.
Okay, so right there, see it?
Pearson.
This is the interactive one right here where you can actually take it and, take it like a test.
Okay.
The one I posted, the PDF copy, is the one we're going to go over together in class.
Okay, thank you.
Yeah, that one you don't have to submit or anything. It's just that that's a static copy that will all have the same one to work on.
Okay.
The prep quiz itself, if you take it in My Stat Lab, it's a question pool, so you get different questions each time.
Awesome. All right, thank you.
Okay, yeah, so this one here is interactive and you can actually go through and answer the questions on the one that's in My Stat Lab. So if you go through the questions, you'll see, here's one that's asking for a probability. So you put the answer in here. And then this is just like a unit test. You have to do all the questions before you get the answers. All right, and you can get to review all the questions and all the answers after you submit it. And if you want to go back and take it again, you can take it as many times as you want.
And this
Thank you.
just to be clear, this is the quiz that if we do get a certain percentage,
Yes.
we get the extra percent. Okay.
Yep.
Thank you.
Final exam prep quiz right there. Okay, and I really encourage you to use it because remember, you're not going to use StatCrunch on the final. So I really want you to see how I'm going to present questions to you with output in them, because I'm not going to have you have to go to StatCrunch and create output. I'm going to put the output there for you that you need to answer the questions. So that's why it's really important for you to try that prep quiz so you see the format of the questions, because some of them are going to be a little tiny bit different than what you're used to seeing because you're not going to use StatCrunch. You won't have to use StatCrunch. You will need a calculator though.
What class are we going to be going over the PDF version of the
Next week.
Okay, and that's if we wait to do the prep quiz until after that class, will we still get the
Yes. The prep quiz, look, it's going to be available here till May 7th. See the date?
Okay, but we have to get it done, or we have to do it before the 4th, right? To get that.
No. What you need to do before the 4th is the honor lock sample test if you want to get the bonus point.
Oh, gotcha. Sorry.
Yeah, that's okay. No, this will be open until your final closes because the final's not showing up yet because it's not available until May 5th. But your final's due on May 7th, and the honor locks, the prep quiz is also due on May 7th at 11 o'clock because I need to get your grades done.
Okay, thank you.
You're welcome. Yeah, you can keep doing it. I mean, even after you take the final, if you say, oh, I need more points, you can go back and still take the prep quiz. It's still there until May 7th at 11 o'clock right there. All right. Anybody else have questions? All right, let me stop sharing for a second and catch up on attendance because I didn't catch everybody coming in. So let me see who I've got. Is Arbonat here? I don't see Arbonat. No. Rochelle, is Rochelle here? I don't see Rochelle. Anthony Figueroa, I have you checked in. Ureli, I have you checked in. Anthony Fusaro, I have you checked in. Adam Gliana, is Adam here? No. Lindsay Hayes? No. Kelly, I have you. Marielle, I have you. Sequoia, are you here? No. Medea, I have you. Julie Klein, I have you. Camille, I have you. Elda, I have. Aude, are you here? I don't think she's here. Jamie Martin, I have you. Kaylin McCarthy, I saw you. Yes, you're here. Christina Myers. Christina here? No, I don't see her. Sasha Lee, I have you checked in. Alexia, I have you checked in. Chanel, are you here, Chanel?
I'm
No.
here.
Chanel's here?
No, Alexia.
Oh, yeah, I got you. I got you.
Oh, okay, thank
Yeah, I
you.
got you. No, Chanel's not here. Lisbeth, are you here? Lisbeth? No. Luke Shaw? Nope. Marissa Smith, I've checked you in. Ashley Smither? Ashley? Oh, she's usually here. Mackenzie Sullivan? No, okay. So I should have 15. 1, 2, 3, 7, 8. Yep, got 15. Okay. I'll check once more at the end of class. Okay. All right. So let's take a look at the material for tonight. Again, this is the last thing that's going to be on your final. And it's in the last unit, unit 6. Remember, last week we did bivariate data. And we did correlation, we did scatter plots, correlation, and regression. This week we're doing bivariate data again, but this time we're looking at categorical data rather than quantitative data. And we're going to look at contingency tables, which we've actually seen before when we did probability, especially when we did conditional probability. We had tables, contingency tables of data, two-way tables, where we have frequency counts for the data. And we have at least 2 rows and 2 columns. And we're going to do a hypothesis test here on the independence of the row variable and the column variable. And you see this used very, very frequently in journal articles. It's called a test for independence of the variables. So again, a contingency table or a two-way frequency table is a table consisting of frequency counts of categorical data. So again, different from what we did last week where we had quantitative. Now we have categorical data corresponding to 2 different variables. One variable is in the rows and one is in the columns. And in the cells, we need to have counts. We can't have percentages or decimals or anything. We have to have counts. So in the test for independence, what we're going to do is test the null. There's no numbers this time. The null in the contingency table that the variables are independent. That is, there's no dependency between the row variable and the column variable. And you'll see with examples, I'll show you what I mean by that. So a couple of things for terminology that we want to talk about. So we're going to conduct a hypothesis test for independence between the row variable and the column variable in a contingency table. So we're going to use capital letter O to be the observed frequency in a cell of the table, and capital E is what we expect to see in that cell, assuming the null is true that the row and column variables are independent. And then we have the lowercase r is the number of rows in the table, and we don't include the labels or the total rows, and C is the number of columns. Okay, we have 5 requirements. Random sample, which we always usually have. Data are counts in the table. I mentioned that before. You have to have counts. Each cell in the table has to have an expected frequency of at least 5. The observed frequencies do not have to be at least 5, but the expecteds do. The sample data are independent of one another, and we have a sample size less than 10% of the population. And so the hypotheses are going to be very simple. No numbers now. Row and column variables are independent for the null. The alternative is going to be actually written 2 ways. It could either be row and column variables are dependent, or may also be written as not independent, because they both mean the same thing. And our test statistic is called a chi-square. So we have a new test statistic and a new distribution. I'm going to talk to you about that on the next page. But what we do to calculate the test statistic we use is in each cell of the table, we take the observed value that we have in the table minus what we expect, square that, and divide by what we expect. So we kind of standardize it, almost like a z-score. And then we add that up for all the cells. And that's called the chi-square statistic. And the expected cell count is found like this. You take, for a particular cell, the total for that, whatever row that cell is in, times the total for the column the cell is in, and divide by the overall total. And I'll do some examples for you in the problems that we're going to go over, so you see how that's done. StatCrunch can do that for you too, but it's also one thing I can ask you to do on the final, because it's a pretty easy calculation. Okay, so the chi-square, kind of like the t-test, has degrees of freedom. And the degrees of freedom here are going to be the row minus 1, the number of rows minus 1, times the number of columns minus 1. So again, like our T statistic, for a chi-square, we also have degrees of freedom. Tests for independence are always right-tailed. We reject the null when we have large values of the test statistic. So let's go back to look at the test statistic for a minute. So what happens here, if the observed cell count is not close to the expected, this numerator is going to get bigger. And when we square it, it's going to get even bigger. And that's what's going to make this large if, in fact, the two variables are not independent. If they're independent, then we would expect the observed and expected to be close together. So it's going to be a right-tailed test, and we're going to reject it when we have very large values of the test statistic. So here's a little picture here. So if the observed and the expected are close together for each cell, then we're going to have a small chi-square value. And the chi-square looks like this. It's a positive distribution. It can't be negative because we square it. We square in the numerator. It starts at 0, and then it goes out here with a long tail on the right-hand side. So if the observed and expected are close together, our chi-square is going to be down here somewhere, and we're going to fail to reject independence. If the observed and expecteds are far apart, then our chi-square is going to be way out here in the tail, the statistic, and we're going to reject. Again, remember that if the p is low, the independence must go. Okay, and again, I mentioned about finding expected cell counts. And again, we'll do some examples in a minute so you see this. So to find the expected cell count for any one cell, you're going to take the total for that, whatever row that cell is in, whatever the total is on the right-hand side, times the column total, so the bottom of the table, whatever column that cell is in, multiply those together and then divide by the grand total. And that tells you what we would expect to see if the two variables were independent. If we reject the null, we state we have evidence that one variable is dependent on the other or not independent of the other. If we fail to reject, we state the evidence does not support rejection of the claim, this sounds familiar, that two variables are independent. But this is one time where your hypotheses don't have any numbers in them. Just going to talk about the variables that you're testing. Okay, so let's try an example. And this one we're just going to do on the paper. In a minute, we'll go over to StatCrunch. So this one has to do with a study of seatbelt users and non-users yielded the randomly selected data summarized below. We want to test the claim, here's our claim, that the amount of smoking is independent of seatbelt use. A plausible theory is that people who smoke more are less concerned about their health and safety and less likely to wear seatbelts. Is this theory supported by the data? Okay, so here's the data. So the two variables we're looking at are seatbelt use and cigarette smoking. And so first we want to write the hypotheses to test the claim that the amount of smoking is independent of seatbelt use. So what you're going to do in your knowledge, you're going to write down the two variables. So amount of smoking is one variable, and the other variable is called seatbelt use. Seatbelt use are independent. So that's going to be my null. Okay, it's always going to say in the null are independent. My alternative is going to be, I'm just going to put dittos here because I don't feel like writing the whole thing out again, that these two variables are either dependent, and some of the problems in your homework, you may also see them written as not independent because they mean the same thing. Okay, so our null is always going to be the two variables are independent. The alternative is going to be the two variables are dependent, or you may also see it written as are not independent because those two phrases mean the same thing. Okay, how many degrees of freedom are associated with this chi-square test of independence? So the first thing you want to do is look at the table. How many rows are in that table? Can anybody tell me how many rows are in the table? I don't count the label rows and I don't count the totals. How many rows do I have in that table? Anybody want to try? How many rows are there? How many rows are in that table?
2.
Yep, thank you, 2. But you don't count this total row and you don't count the rows up here with the labels on them. And then how many columns do I have? How many columns are there? Anybody want to try? How many columns do we have?
4.
4, yep. So the degrees of freedom are going to be r minus 1, so 2 minus 1, times column minus 1, 4 minus 1. So 2 minus 1 is 1, times 3. So this table has 3 degrees of freedom. Okay, and the reason you need to know that, if you weren't using technology to look up your critical value, you'd have to know how many degrees of freedom it has. But this has 3 degrees of freedom in it. Now we're going to do an expected cell count for one of the cells in the table so I can show you how this works. And we're going to do it for no cigarettes smoked and wear seatbelts. Okay, so no cigarettes smoked and wear seatbelts. So it's this cell right here. Okay, so my formula says I'm going to go in there and I'm going to get the row total. So look at the row here, it's in this row. And I go over here and I find the total number of people in the table who wear seatbelts, 243. And then I go down the column that's in and I find the total number of people who didn't smoke any cigarettes, 324. And then I divide by my grand total, which is 459. Okay, so row total times column total over grand total. And then just simplify that in your calculator. It probably doesn't come out to be an integer, but
Where did you get 243? I'm sorry.
right here.
Okay, what was the 175 for?
That's the cell we're finding the expected cell count for. The problem said, what's the expected cell count for no cigarette smoke per day and wear seatbelts? That's the cell I'm getting the expected cell count for. So that tells me how to orient myself in the table. So it's in this row. So there's my row total. It's in this column. So there's my column total.
Oh, gotcha.
See it? And then I divide by the overall.
Alrighty, thank you.
Because if the 2 variables are independent, what this tells me is how many people I would expect to see in that cell. So let's see what it works out to be, and then we'll look at what it was and see how close they are. So we're going to take 243 times 324, and we're going to divide by 459. And I get 171. I'm going to just put one decimal, 171.5. Okay, so I would expect to see about 172 people, and I actually saw 175, so it's pretty close. Okay. So everybody understand how I did that? So first you want to identify the cell they're asking you to find the expected cell count for, located in the table, and then your formula is going to be the row total for the row that cell is in, whatever that total is, times the column total for the column where that cell is, and then you're going to multiply those together, and then you're going to divide by the grand total. All right. Now, this time I've given you the chi-square and the p-value. So the chi-square for this table or for this test is 1.36 with a p-value of 0.7154. We use the same rules we used before. At alpha of 0.05, do we reject or do we fail to reject? Who can tell me? So remember, one of my little acronyms for you to remember, PLAR, p-value less than alpha reject. Is this p-value less than 0.05?
No.
No. So therefore what's our decision?
Fail to reject?
Fail to reject. Yes, we fail to reject. So what's our conclusion? So remember my little flow chart I had there for you before. Let's go back for a second. So when we have a p-value where we fail to reject, we're going to say fail to reject, and we're going to conclude further down the page here. Evidence does not support rejection of the claim that the 2 variables are independent. So we can't reject the claim that these variables of smoking and seatbelt use are independent. So it doesn't seem that the theory is upheld here. The theory was that people who smoke more are less concerned about their health and safety and less likely to wear seatbelts. Our data, the chi-square test does not support that, because we're saying there is no relationship between wearing seatbelts and the number of cigarettes smoked per day. One way you can look at this too is look within, it's always kind of interesting to do this. Let's look across this way. Let's look at the percent of people in each of the cigarette categories. This is the percent that wear seatbelts. It's always kind of interesting to look at this. So if I take 175 and I divide by 324, let's get the percents across there and you can kind of see where this is coming from. Actually, I think I want to do it the other way. I'm going to do it over here for don't smoke. I think it's more interesting here to do it this way. I'm going to do it for don't smoke. I'm going to take the people who don't smoke divided by the total in each of the two columns. Let's do it that way. I think that's more interesting. 175 divided by 243. 72% of people who don't smoke wear their seatbelt. And then I'm going to take 149 and divide by 216, and I get 69% of people who don't wear seatbelts don't smoke. These percentages are just about the same. If there was an effect, if there was a relationship between the variables, you would expect to see different percents here. You might expect to see this percent be much higher than this percent here. So that's another way to look at a table. We're going to look at a table in a minute that way on one of the examples I have to show you.
All right, can I see the percent again?
Mhm.
And what question were you doing the percentages for, like getting them?
I wasn't. I was just saying it's another interesting way to look at the data in the table. I didn't ask you a question about it.
Okay, all right.
Just interesting. I think you have some problems in your homework where they do ask a question like that. So that's why I wanted to show it to you. But this is an interesting way to drill into the data. You could also do it this way. You could do 175 over 324. Let me do those real quick and so you can see these are not going to be much different either. 324. I got 54%. And then 20 divided by 37, 54%. So this is the percent in each group of the different cigarette numbers smoked who wear seatbelts. 42 divided by 83, 51%. And finally, 6 divided by 15. This is a little low because that's a small sample size. This is only 40%, but that's a really tiny sample size. But if you notice here, it's pretty consistent that the percentage of people wearing seatbelts seem to be about the same no matter whether they smoke cigarettes or not. So that's also another interesting way to look at data in a table. Again, it's not on one of the questions on the page, but I'm just showing you how people, this is what we call drilling into data, kind of what we did with conditional probabilities way back in chapter 4. Okay, so let's do another one. Oh, here I'm going to do some from the homework. Okay. Yeah, so this one I'm going to pull up the question from that has a similar question like this in the homework. So let me go to your homework on this section and show you a problem here, which is kind of interesting. Let's go back to homework. And chapter 11. So I want to do problem number 5. Nope, not that one. No. Go back. Come on. Here we go. Okay, you don't have that many problems in here. Problem number 5. This one has quite a few parts to it. This is actually a nice review question for you before the final too, because it goes through a lot of things that you learned back in probability section. So we have a table. It shows who survived the sinking of a ship based on whether they were crew members or passengers booked in first class, second class, or third class. So here's the table here. Survivors were the people who were alive. The people who died were called dead. And then there's the 4 classes of people. And they ask you a couple probability questions first. So let's go through these together. If an individual is drawn at random, what's the probability they're a member of the crew? Okay, so this goes back to your basic probability that you had back in chapter 4. So crew, so what you're going to do here is look at all the crew people in my table, 955, and I'm going to divide by the total in the table. So let me get my computer calculator up here. All right, so I'm going to take the 955, and I'm going to divide by the total in my table, which is 2517. And so the probability for me is how many decimals? Oh, they want a percent. So I'm going to multiply by 100. So 37.9% of the people on the ship were in the crew. So 37.9. Okay. Now we want to look at what's the probability of selecting a third class passenger who survived. So now you're going to go in for one of the cells of the table. So third class passenger who survived. So right here, 213, and I'm going to divide by 2517. Okay, so I'm going to take 213 and divide by 2517. And so now I've got multiplied by 100. Oh, I did something wrong. Hold on a second. Let's try this again. 213 213 divided by 2517. Oh, 2517. Forget it. Oh gosh. 2517. There we go. That's better. I don't know what I did before, but I certainly had the wrong answer. Times 100. So I'm still getting something wrong here. Oh, what am I doing wrong? Try it again. It was 8 point something. 213 divided by 2517. Nope. 2517. There we go. 8.5%. I'm just going to type in 8.5. I don't know what's going on with this calculator, but it's not cooperating tonight. It should be 8.5. There we go. Okay. Now, what's the probability? Now, here's a conditional probability. What's the probability? And again, remember way back when in chapter 4, what's the probability of a randomly selected passenger surviving given they were first class? All right, so we're focusing on the first class people. And we want to find the probability that a first class passenger survived. So what are we going to do? We're going to focus on the 419, and how many of those survived? 236. So we're going to take 2, 3, 6, and we're going to divide by 419. 419. And I think they want a percent again, 56.3%. Yep. Now, before I go on to the next question, let's look at, so that was for first class. Let's look at the crew. So what's the probability a person survived given they were a crew member? So now we're focusing on this column here. Again, this is your conditional probabilities from chapter 4. So let's go ahead and calculate that probability. So if probability of a crew member surviving, a person surviving given they were a crew member. So we're going to take 237, and we're going to divide by the total number of crew, which is 955. And now we have it 24.8%. So compare that to what we just calculated for the first class, which was 56.3. So do you think there's a relationship between these variables? Who's more likely to survive on the ship? Who was more likely to survive from the numbers I just showed you? Anybody? Would you rather be a crew member or would you rather be in first class? I think I'd rather be in first class.
Plus.
Right? Because it's twice as high the survival rate as the crew members. So this is the kind of thing you're going to see when there is something going on in terms of the, and the chi-square statistic here is, I don't know if we do it on this problem or not, but it's definitely going to be significant. All right, let's take a look at the next question, because the next question asks you, if the two variables were, if the person's chances of surviving were the same regardless of their status on the ship, this is, you want to find basically an expected cell count. How many members of the crew would be expected to live? So they're asking you now to find the expected cell count for the cell right here, that 237. So what did we do before? We took the row total. Look at this out. So we're looking at this cell here, 237. So the row total for that row is 853, 853 times the column total, which is 955. And we're going to divide by the overall total, which is 2517. Okay, so if the two were independent, we would expect to see in this crew cell right here for alive about 324. How many decimals do they want here? Hold on a second. 2 decimals. So 323.65. 323.65. So you're seeing, this is where you see the impact of things not being independent. And we just said it. It seems like it's better to be a first class passenger than a crew member. So we only had 237 crew members survive. But if the two variables were not related in any way, we would expect to see about 324 crew members surviving. So we're seeing far less than we expected. So what's the null and alternative? Okay, so remember what I said before, you're going to look at the two variables we're looking at, which are survival and ticket class. And your null is always going to be that they're independent. And your alternative is either going to be they're not independent or they're dependent. So let's take a look at our choices here. I'll move my tools out of the way so we can see the choices. Survival was independent of status on the ship. Passengers were more likely to live. Okay, we never have a direction in our alternative for this. We always have the alternative being either not independent or dependent. So survival was independent of status. Survival was not independent of status. That looks pretty good. C's got them reversed. But remember that null always says that the two variables are independent, so it can't be C. And again, D is giving an alternative with some kind of a direction to it, and we don't say that. We can't do that with this kind of a test here. So the right answer here is going to be this one. The two variables are independent for the null, and the alternative is that they're either dependent or not independent. Okay, and I don't know if there's another part here. Degrees of freedom. How many degrees of freedom for this test? So our degrees of freedom were row -1 times column -1. So how many rows do we have in the table?
3.
How many rows? Well, that's all right. Let's do rows first.
Yeah.
You don't count the total row.
Oh, 2.
2. Okay, so 2 minus 1 is 1. How many columns do we have?
4.
4. Yeah, don't count the labels and don't count the total. So 4. So 4 minus 1 is 3. 3 times 1 gives us 3 degrees of freedom. All right, and oh, they did this. Okay, they did the work for you. The chi-square is 161.7 and the p-value is barely greater than 0. So let's say we were using a significance level of 0.05. Would we reject or would we fail to reject? We have a really tiny p-value. So what are we going to do? Reject or fail to reject?
Reject.
Yeah, we're going to reject. So we're going to look at C and D. So when we reject, we always say what? There is, which one? C or D?
Sufficient.
Yep, always sufficient. Yep. Same way that you had your conclusions written before, but you don't have numbers this time. This time you're saying that the two variables are somehow related or dependent or not independent. You'll see different wording sometimes in the questions. Okay, so that's a nice review question for you. Okay, let's do number 6. This one right here. So we have the table below includes results from a polygraph lie detector experiments conducted by researchers. In each case, it was known if the subject lied or did not lie, and the table indicates when the polygraph test was correct. So you can open up the table here. Now I'm going to show you, we're going to actually go into StatCrunch and do this work in StatCrunch. Okay, so first thing we want to do is what are the null and alternatives? So let's take a look at the possibilities here. So remember the two variables that we're looking at are subject lying and polygraph result. Yeah, those are the two variables. Yeah, let me look at the claim again. Test the claim whether the subject lies is independent of the polygraph test. Okay, so the two variables are subject lies and polygraph test indications. So let's take a look here. Okay, so we're not testing whether the polygraph testing was accurate. That's not correct. So you can eliminate B and C. Your null always has to say the two variables are independent. So therefore, the right answer here must be answer
A.
A. Yeah. Okay, so we got that part. All right. Now, what we're going to do is we're going to go into StatCrunch, and I'm going to show you how to use StatCrunch to find the chi-square statistic. So you've got a little data table here. And once it opens up, okay. So what you're going to do for your chi-square test is you're going to go to Stat, Tables, Contingency with Summary. Okay, now the columns that you're going to select are the columns with the counts in them. So if you go back and look at my table here, oh, I can get this down a little bit. Okay, let me make this bigger so you can see it. So up top, you're going to select the columns with the counts. So my columns with the counts are did not lie and lied. So I'm going to select those two. The row labels here are over here. And in this example here, there's no name to it. It just has a dash there if you look carefully. So it's the column labeled with a dash. Now down here, Let's go ahead and get the expected cell count so you can see that. StatCrunch will do that work for you. And then down here, you just want to leave it the default to the chi-square test for independence because that'll come out. That's what you want right there. But I want you to see the table with the expected counts. It's always interesting to see. And then just hit compute. Okay, so the first thing I'm going to do is make sure the data went anything the way you think it should. So 19, 36, 16, 14. So it looks like good to us. Okay, so look what we have. So we have, here's my table here, and here's the expected cell counts below. So this is expect to see, if the two variables were independent, we would expect to see about 23 people here, and we had 19. We'd expect to see 32 here, we had 36. These are pretty close. So let's scroll down a little bit further. Here's my chi-square, 1 degree of freedom, because we have 2 rows and 2 columns. So 2 minus 1 is 1, 1 times 1 gives me 1. Here's my p-value, 0.0926. And the first thing the question asked me to give it was the chi-square rounded to 3 decimals. So here's my chi-square right here. That's my test statistic right there, 2.829. So I'm going to go ahead and put that in. Let's get rid of this. Oops. 2.829. And then they want the p-value and they want 4 decimals. Oh no, where'd my output go? Hold on. Here it is. And my p-value was 0.0926. Excuse me. 26. All right, and we are testing 0.05. All right, so we have a p-value of 0.0926 and we're testing at 0.05. So what do you think? Are we going to reject or are we going to fail to reject?
Fail
to
to
reject.
Fail to reject. So when we fail to reject, what do we write in our conclusion?
not sufficient.
There's not
evidence.
sufficient, right? Not sufficient evidence. So let me see. Oh, hold on a second. Sorry, I didn't mean to do that. I was trying to get my tools out of the way so I could see the answers. There's not sufficient evidence to warrant rejection of the claim that polygraph testing is 95% accurate. Wrong. We don't do anything like that. We're only testing whether the two variables are independent. There's not sufficient evidence to warrant rejection of the claim that whether a subject lies is independent of the polygraph indication. That's the right conclusion. Okay, everybody see that? And then we'll just check it, make sure we got it right. Okay, and then I was going to do number 11. Let's try another one where we do actually do the chi-square. You don't have that many problems to do in this section. Okay, so this was a study. It was a retrospective study. Remember retrospective studies? Good review for you for the final. Way back in the first unit, was conducted to investigate a relationship between the colors of helmets worn by motorcycle drivers and whether they were injured or killed in a crash. So here's the data in the table. And so we have 5 colors, and then we have whether or not they were killed. So we had controls that were not injured, and then we had cases that were either injured or killed. And then we have it broken down by the color of the helmet. So the first thing we want to do is write the hypotheses. Okay, so the two variables we're looking at are, what are they going to call it? Injury, I guess. Oh, crash occurred. Whether, no, not crash occurred. It's whether they were injured or killed. Let's take a look here. Oh, they're calling it crash occurred. Oh, crash occurred. Let me get back and look at this again. Wording is a little odd because up here it says the color of the helmets and then whether they were injured or killed in the crash. Okay, I don't really see where it says whether the crash occurred, but it looks like those are the variables they're using here. Oh, no, injuries are here. I'm sorry, I missed it. Yeah, their injuries are here. Yeah, so they're not really looking at whether the crash occurred. That's why I had to take a look at the question again. They're looking at whether or not the people were injured. And the injuries are either not injured or killed. So those are the two categories. So we're actually going to focus on B and C here because we're looking at injuries and helmet color. And we're looking at the null always has to say the two variables are independent and the alternative is either not independent or dependent. So we're going to pick C. Oh, I think this is one of the ones I edited a little bit. So you have to go through the whole question before you get the answer. Answers checked. Okay, so let's go ahead and get the chi-square. So let's go ahead up here and open up the data in StatCrunch. Same steps that we did before. So we're going to go to Stat, Tables, contingency with summary. Now you're going to pick the columns with all the colored helmets all the way down here. And then the row labels here happens to be called var1. It doesn't have a name at the top of it. It's just called var1. And let's just get the chi-square. Okay, so there's my table. I always like to make sure it put the numbers in the way I thought it should. Yeah, it looks good. Okay. And here's my chi-square down here. Here's my p-value. So let's take a look at the question. How many? They want 3 decimals. Let's pull this up. So my test statistic is 10.380. And again, you can't, this one you're gonna have to go all the way through. I edited some things out of the question. That's why it's making you do all the parts before it checks your answers. And then finally, they want the conclusion. So, and the p-value is, you're gonna have to look at the problem for the p-value. The p-value was 0.0345. And the alpha level they asked us to use was 0.05. So we're going to reject, right? Because 0.035 is less than 0.05. So we're going to reject the null. And we always say there is sufficient evidence. Yep. And check. Yep, there we go. Yeah, that's a weird one because I did the question. I can't remember. I took something out that we don't cover. I think I got this question from another textbook. Oh no, I created the question. Anyway, when I create questions, you have to do all the parts before you get to check it. So I wanted to show you that one. Now I'm going to go back to the paper because I have an interesting problem on the handout that I wanted to go over with you because this is a real world example and I like this problem. So let's go back onto our paper and where did I put it now? Oh no, did I lose my problem? Where is it? Bear with me, it's here somewhere. Here it is. Okay, so this is a true story. This is a true set of data here. And I thought it would be interesting because many students in here I know want to go into nursing. So I thought this is an interesting one to go over with you. So it says, alert nurses at the Veterans Medical Center in Northampton, Massachusetts, notice an unusually high number of deaths at times when another nurse, Kristen Gilbert, was working. These nurses later noticed missing supplies of the drug epinephrine, which is a synthetic adrenaline that stimulates the heart. Kristen was arrested and charged with 4 counts of murder and 2 counts of attempted murder. When seeking a criminal jury indictment, prosecutors provided a key piece of evidence consisting of the table below. Use a 0.01 significance level to test the claim that the deaths on shifts were independent of whether Gilbert was working. What does the result suggest about guilt or innocence of Gilbert? Okay, so I didn't actually write any questions down here, but let's write the hypotheses first. So our hypotheses, so the 2 variables we're looking at are Gilbert working and deaths with shifts. So the null is going to be Gilbert working and shifts with deaths are independent. And our alternative is going to be that the 2 variables are, I like the words not independent. I don't know why they just sound better to me, but they could also say are dependent. Both mean the same thing. All right, now I'm going to have to take a break just for a second because I forgot to put my data into StatCrunch because I want to do this problem for you in StatCrunch. So just bear with me for a second. I'm going to get a StatCrunch. Yes. Why can't I see? Hold on just a minute. Can't seem to get a. Okay, bear with me just for a minute. I'm trying to get a blank StatCrunch sheet here and I'm not able to do that. Wait a minute. All right. I forgot to put the data into StatCrunch before class started. Just take me a minute to do that. Because we want to do the analysis in StatCrunch, obviously. Although I do want to do a couple things with you by hand, but let me put the data in first. So Kristen working and then shift with death. Shift with okay. Yes. What do we have? 40, 217, and now, and 34. Oops, 34 and 1350. Okay. All right. So before we go to the stack crunch, let me go back to the paper for a second, because what I want to do is take a look at some of the percentages in here. So let's take a look at, this was kind of when I was drilling into their table before. Let's look at, let's see which way is more interesting to look at. Shift with a death. Let me see. I'm trying to figure out which way would be more interesting for you to look at. Let me just check it real quick this way. Oops. No, that's not right. Okay, let's look overall at the percent of shifts with a death first. So let's take 74 and divide by the total number of shifts. Okay, so I'm going to take the 74 here. So this is percent overall of shifts with a death. So to do that, I'm going to take there were 74 total shifts with a death, and I'm going to divide that by the total number of shifts they looked at, which is 1641. Let's see what we get when you do that. So 74 divided by 1641 gives me comes out to be about 4.5%. Okay, now let's look at the percent of shifts with a death when Kristen was working. Okay, so that's going to be 40 over 257. So if I take 40 and I divide by 257, I get 15.6. And then if I do the percent of the shifts with a death when Kristen was not working, let's see what we get, which would be 34. 34 over 1384. 34 divided by 1384. 2.5%. Okay, so before we go look at the chi-square, what do you think about those numbers? So overall, about 4.5% of shifts had a death. If we just focus on the shifts when Kristen was working, the percent of shifts with a death is 15.6%.
So it went up a lot when she was working.
It sure did, right? And then if we look at the shifts when she wasn't working, it's down to 2.5%. So pretty interesting, which leads us to think that maybe when we do that chi-square, we're probably going to get we're probably going to reject our null that these are not independent. All right, so let's go over to StatCrunch. I put the data into StatCrunch so we could go ahead and do the chi-square. Those are the kind of things that you would want to look at that would lead you to think maybe something is going on. So I just took the data and I put it into the spreadsheet right here in StatCrunch. So we're going to go to Stat, Tables, Contingency with a summary. And we're going to use the deaths with a shift, have the counts in them. And then I put the labels in the column labeled Kristen working, yes or no. And we'll just get the chi-square. Actually, let's do the expected cell counts too, because that might be interesting for you to see too. All right, so what do we get? So look at the expected cell counts. It's pretty dramatic here. So we would expect if the two variables were independent, when Kristen was working, we would only expect to see about 12 shifts with a death and about 245 without a death. But notice we had 40 with a death and only 217 without a death. And if you go down here, look at my chi-square, it only has 1 degree of freedom, and the p-value is less than 0.001, 0001 rather. So what would be our conclusion here? Would we reject the null that the two variables are independent?
Yeah.
Yes, we would, definitely. And this data is real data. This particular person, actually, if she's still alive, this happened back in the 1980s. She was sentenced to life in prison. This happened in Massachusetts. And she was sentenced to life in prison. And I don't know just based on this data, but this data was given to the grand jury in order to bring the indictment, which of course precedes actually going to trial. But I would assume that whoever took this to the grand jury would know how to drill into the data, so you would show numbers like this. And it's pretty impressive that there was definitely a huge increase in the rate of deaths on the shifts when this nurse was working. So pretty interesting. Okay, so let me stop sharing for a second. So that's the material for tonight. Oh, yeah, we pretty much did the problems too. I don't think there's any other homework problems to go over with you, because you don't have that many to do. Questions on what we did tonight. So we did the chi-square test for independence, 2 categorical variables in a contingency table. The null and alternative are basically always going to be the same. Null is always going to be the 2 variables are independent. Alternative is going to be they're either not independent or dependent. You're going to use StatCrunch to get your chi-square. You're going to make your conclusion just like we did. Some problems will ask you to do the expected cell count like I went over with you. And that's pretty much it. You don't have that many problems to do for your homework. I think I went over more than half of the ones that are in there. All right, questions on what we did tonight. And then I'll take questions from your homework that's due tonight, which is 2.4, 10.1, and 10.2. Oh, let me check attendance again too to see if anybody else came in. Let's see. I think I have everybody, but let me just check and see. Did Arbonat come in? Rochelle come in? I'm not calling your name. I have you checked in. Adam. Lindsay Hayes. I don't see her. Sequoia. Oh, Sequoia's here. I gotcha. Auday. Christina. No. Chanel. Lisbeth. Nope. Luke. Nope. Ashley. Or Mackenzie. No. Okay. All right. Okay. So questions on what we did tonight. If no questions there, then I will take questions from your homework due tonight.
I have a question on number 11 from last week's homework.
Okay, hold on just a second, Anthony. Let me get it pulled up, okay?
Yeah.
All right, so let's go back. If you don't have any questions, you can leave and I'll see you next week, okay? So let me get to the homework. StatCrunch. Okay. Anthony, which section now?
Section 10.2, sorry.
Okay, that's okay, because we have 3 sections. So number 11?
Yes.
Okay. Okay, this one here?
Yeah.
All right, so this was the one for the twins and the IQ, right? This is the right one?
Yeah.
Okay, so what happened when you did it? You didn't get the answer that they wanted, or?
No, I didn't. I was off, but I thought I was doing it right. I did the on yours it would be the 4.05 plus 0.94 times.
Let me take a look at your work. Is it still there? What got marked wrong?
I reset the question.
Oh, okay, because I was going to take a look at what you did. Okay, because sometimes it helps me to see it. That's okay. All right, let me share a screen again. Okay, because sometimes if I can see what you did, then I can try to figure out maybe where. So it was number 11, right?
Yeah.
Okay. All right, so let's see. So here's our equation right here, and we want to find
The IQ of 95. So so you would do 4.05 plus 0.94 times 95.
No, careful. So you want to take, let me clear this out. You want to take the slope first. So you're going to take the 0.94 and multiply by the 95 first, and then add the 4.05.
Oh, okay. I must have just forgotten like the order.
Yeah. Order of operations. Multiplication takes precedent over addition. So you're going to take the IQ they gave you was 95. Oh, I hate this computer. 95 times the slope here is 0.94. And then we're going to add 4.05. 4.05. This may not be the problem you got, but so I got 93.35.
Okay, that makes sense.
It sounds like you didn't do the right order of operations. That's why I was hoping yours was still there so I could see it. Yeah.
Yeah, I just didn't do the right order.
Yeah. Okay.
Thank you. And then
You're welcome.
I have to talk to you after class.
Okay. Okay. All right. Other questions from people who are still here?
I have a question on 11.2, number 11.
That's what we just did.
11.2?
Yeah. The IQ scores.
No, section 11.2.
Oh, 11.2. Oh, the one we just did tonight.
Yes.
Oh, I'm sorry. Okay, hold on just a second. Come on.
Thank you. Question 11 was actually the one I needed to ask about as well.
Oh,
so.
good. Okay, so maybe you
Thank
did
you
the
for your
same
time
thing he
tonight.
did. Okay. You multiply the number given times the slope and then add or subtract the y-intercept, okay?
Okay, thank you.
Yeah, it might have been
Bye.
order of operations. Okay.
See you next week, Professor.
Okay, bye. All right, so number 11 here on 11.2. This one here?
Yes.
Okay, we just did this one.
I redid my problem and it still said I got the wrong the test statistic. Like I substituted it in and everything the way it's supposed to be done, but I'm not sure
Is your wrong problem still there? Or did you regenerate
yes,
it?
it's still there.
All right, hold on just a second. Let me stop sharing. And wait a minute, wait a second. Stop sharing. Who's asking me the question?
Sequoia Hyman.
Sequoia. Okay. All right. I couldn't tell who it was. Okay, hold on a second.
Sorry.
That's all right. It's easier if I can look at your question so I can try to see what happened.
I got all the other parts right, but I'm not sure, like being that I use StatCrunch, I'm not sure how I got that part wrong. Like, did I substitute something wrong, or did I not put everything in a proper place, or I'm not sure what happened.
Let me see. All right, so just take me a minute because I'll run the this chi-square test first. Tables, contingency with summary. Okay, there one. Okay, all right, so let me see what your answers were. Because it looks like you got most all of it right. You got the test statistic wrong.
Yeah, that's what I'm saying. Like, I'm not sure if I plugged in something incorrectly or what it was.
I have a feeling maybe you didn't highlight all the columns with the colored helmets.
It was yellow, red, and black, I think it was.
Well, there's 5.
Okay, that's probably
because I'm
it.
looking at Sequoia, I'm looking at your chi-square and it was 8.2 and the right answer is a little bit more than 10, which says to me that you may have only highlighted 4 color columns instead of 5.
Okay, then that makes a little more sense.
That's probably what you did. Yeah, usually I can troubleshoot a little bit, but looking at how different your chi-square is, it looks to me like you didn't, yeah, I'll bet you didn't,
highlight all the colors.
You didn't highlight, yeah, because you had to go down a little bit further because there's so many colors in.
Oh, okay.
And so if you don't go all the way down, you don't pick the 5th color, and I'll bet you only pick 4 colors.
Yeah, because I seen that the little dash right above it, so I thought
that's for the label. Yeah, that's for the second part of the where you specify the labels. But at the top one, there should be 5 colors, and I bet you anything you didn't highlight the last color.
Okay, then thank you, Dr.
So if you want to redo it, I mean, you got a great score anyway. But if you want to redo it, that's I can guarantee you 99.9% that's what happened. You didn't pick the last color.
I'm gonna be overachiever and redo it.